So we're now going to look at examples where projectiles and projectile motion is combined in with collisions. So we can apply a knowledge of single body collisions to projectiles which bounce. The key thing to remember, as the same thing with normal single body collisions, is that the vector component switches after collision with either a flat floor or a wall, and we won't be dealing with projectiles that land on angled surfaces. So a key thing to note is that if we have a floor and we have a falling particle, and I'll draw one with a wall. So if we have a falling particle with some y and x velocity, so its velocity will be vx times I plus vy times j. Then after it bounces, the horizontal component will change. Now the horizontal component will stay the same. The vertical component will change by a factor of e. So this is our initial velocity. I should have actually labeled this as initial instead of final. So this should be u. So v, therefore, will be, well, the vxi is staying the same, but we have e times vy times j. So that's if it collides along a floor. So this is for floor. For a wall, if we have the initial velocity as vx times I plus vy times j, the new velocity along a wall will be, well, if you can imagine it hitting off the wall here, the vertical component will stay the same because there's no force acting on that, but the horizontal component will change. So it will be, well, this should actually be minus because it's switching. So minus e vxi plus vy times j will be the new velocity of a particle that's after hitting a wall. So if you can combine certain projectile motion knowledge with the collisions knowledge from single body stuff that you already know, these questions should be fairly straightforward.